Good morning, students. Today's topic of discussion is deep Boltzmann machine. In our last class, we learned about a variant of restricted Boltzmann machine, which is known as a deep Boltzmann machine, which has got more than two layers. This is visible layer, and these three are hidden layers. We looked at the difference between DBN and DBM. DBN is a deep belief network that is also based on RBM, and deep Boltzmann machine DBM has got layers of RBM. This is DBM and this is DBN. DBM and DBN both uses latent features and both perform greedy layer wise training, and both does a discriminative fine tuning after training done by greedy layer wise approach. And both the DBN and DPM uses a large set of unlabeled data for pre-training. Unlabeled data implies that it is unsupervised learning mechanism. For pre-training and apply tuning on a small labeled data set. It makes some changes. It improvise the things. Okay, those were the similarities, and these are the differences. Deep belief network has top two layers with undirected connections, and lower layers have directed connections. Here, these are directed connections, and these are undirected connections. Whereas DBM, all connections are undirected. DBM has all undirected connections. And approximate inference procedure for DBM uses a top-down feedback in addition to usual bottom-up pass. You know, if you represent the model in this manner, then it is top down and bottom up, two passes like we have in this format, forward and backward pass. Here also you have top down and bottom up passes. And the Boltzmann machine incorporate uncertainties better. And a disadvantage of DBN is the approximate inference is based on mean field approach, which is quite slow compared to the bottom up pass used in DBN. Um, okay, this is Comparing Debian only with itself by having a single bottom up pass and comparing these two things. Mean field approach. Mean field approach is slower than a single bottom up pass in Debian. So Debian has two methods. This method is slower than this method. And mean field inference needs to be performed for every new test input. Because of that, it is slower. That method, that Debian particular way of training. What is this mean field or variational approximation? It is nothing but computing posterior distribution. Posterior distribution is also known as inference problem. There is a data distribution P of x and an approximate distribution Q of x is generated that is quite close to the actual distribution. This actual distribution, and then posterior distribution is approximated, and it is you know it can be determined that this distribution which is approximated is the best approximation of p of x, and q of x becomes the mean field approximation where variables in q distribution is independent of the variable x. X is independent variable. Whenever there is a data set, variable 1, variable 2, variable 3, if you call this variable 3 as the class, then this is known as a dependent variable, and these two are independent variable. And here what it says is that qx becomes mean field approximation where variables in q distribution is independent of variable x. And here the goal is to minimize the KL divergence to approximate the distribution and reduce the differences between the actual distribution and the computed distribution. How is this DBM trained? DBM is trained uh, by using randomly initialized Markov chains. Markov chain that represent the events in this manner in some format. That Markov chain is randomly initialized, and then the approximate distribution is computed. And DBM uses greedy layer by layer pre-training to speed up the learning of the weights. And it relies on learning stacks of RBM with a small modification using contrastive divergence. I recall that RBM was trained by using an algorithm known as contrastive divergence. This contrastive divergence algorithm has been modified a little bit uh, to, to train DBM, Deep Boltzmann machine. Here the key intuition for greedy layer wise is that we double the input for lower level RBM and the top level RBM. Here this is lower level RBM and this the top level RBM. Input is doubled. Lower layer RBM inputs are doubled to compensate the lack of top down input. And similarly, a top level RBM hidden units are doubled. Here you see these are the visible nodes. These are the hidden nodes. These are hidden layers. This visible layer. Uh, this is weight. This is uh, double the weight. Weights are doubled, and inputs. You see this. These are the inputs. Inputs are also doubled here and here in the on the top layer and the bottom layer. Weights are doubled in the intermediate layers. So this is how um, DBM model is um, organized in order to train. And finally, the three RBMs are then combined to form a single model. Here, this is RBM1, RBM2, RBM3. Recall that RBM has got only two layers. This is visible layer and this one hidden layer. This is one RBM. The second RBM is this part. Third RBM is this part. These are the three RBMs. When you stack them up, they form a single DBM. And greedily pre-training the weights of the DBM initializes weights to reasonable values such that the joint learning of all layers is made efficient. This is expensive compared to single bottom-up inference used in DBN. In DBN, single bottom-up inference, it is like not having that double layers and double weights. That is single bottom-up inference, and that is uh, you know less expensive compared to this model where you have double weights, double inputs are doubled. To accelerate the inference of DBM, a set of recognition weights are used found by greedy pre-training. Greedy pre-training finds set of weights. Those weights are subsequently used to perform inference, which is nothing but that um, generation of posterior distribution. That one can be made faster if the weights obtained from the physical uh, pre-training weights which are obtained from the pre-training, you use them for inference as well. And here input vector is taken, and then the recognition weights which are obtained from the greedy pre-training are applied to reconstruct the input V. of fully factorized approximation posterior distribution. Each layer of hidden units is activated in a single deterministic bottom-up pass, as shown in the figure. In this figure, it is shown that each layer of hidden units is activated in a single deterministic bottom-up pass. You can see this one. This is bottom-up pass. It applies this V into this weights here denoted by R, and then taking the sum over all combinations and applying a sigmoid. Likewise here also same thing. Here also same thing. So then we apply k iterations of mean field to obtain mean field parameters that will be used in the training update for DBMs. And this one is the uh, equation given for mean field posterior distribution and factorial posterior model. So this is H hidden unit or hidden layer, a condition on V visible layer, and this is mu. This mu is the result of mean field inference, and then V is the guess of the in guess of the input. And by updating the recognition weights, KL divergence is uh, there is an actual value, there is a generated value. So if you subtract this, and if you could reduce the difference, uh, you can say that this generated value is approximately equal to actual value. And then here H condition on V using mu, and this one is H condition on V using V. And finally, to perform classification, we need a separate multi-layer perceptron on top of the hidden feature extracted, and um, that particular layer will perform the classification, and that layer can be fine-tuned as it is done in DBN. Okay, this is about DBM, and we have done with our unit 4. Tomorrow we will start unit 5, variational autoencoders. We looked at the restrictive Boltzmann machine, and then MCMC, Gibbs sampling, gradient computations in RBMs, and deep Boltzmann machines. These are the generative models. Tomorrow we'll begin unit 5 with variational autoencoders.